Okay, this is the question that we are going to work today. This question is from general topology. So in part A, we have to prove that the given set is closed, and in part B, we have to find a continuous function which satisfies this certain condition. Okay, first of all, let us try to understand that what what this set is. So here there are two spaces actually, and x and y, two topological spaces. So we don't know about the topology in x, but they are given us that the topology in y is ordered set topology. So we have to take that fact into the proof. So in part A, we basically goes with the flow. That means that in topology, the most basic ways to prove some set is closed is by looking the complement of that set. If the complement is open, we say that the original set is closed in that particular space. So, so our goal is to uh, look into this the complement of this particular set and see whether we can come up with something. So first of all, let us name this set. Let S to be the given set X and satisfy this certain condition, which means not that, please note that this set is a subspace of x, not y, because the terms are here is x. So and not in the codomain, it's rather in the domain. So it satisfied this condition, which means the image image under f is less than image under g. What are these f and g? These are continuous functions between two topological spaces. So we have to take that fact into the account as well. So here I first name this set as S. It just I gave a name for this set. So now I have to consider the complement of this set. So what is the complement means? The complement means that all the elements in the main space that are not in our considered set, which means all the x in capital X that not are in capital S. Okay, so complement we denote like this. So you can, for easiness, you can name this as A as well. No worries there. So this also a subset of X. Now, what are the elements that are in X that not in capital S? So, if some simple X satisfies this condition, then it should belong to a capital S, which means if some X is like this, let's say X naught, some X naught satisfies this condition, we can put X naught into this set. But so it can't belong to the complement of S because it's already in S. So we have to take the negation of this one in order to form the complement. That's my point. Because if some X is satisfied this condition, it can't belong to the capital S. It's rather belong to the complement of this one. So we are going to prove this set is open. Our goal is to prove that this set is open. Okay. So in order to prove this set is open, I'm going to take two elements from, sorry, I'm going to take an arbitrary element from this set. So let x in A. So by x, I denote any element in the complement of S. So my goal is to prove that this set is open. So in a way, along the proof, I should find an open set that's open set that contains in A, and also all the x's should come from that open set. So if we can find such open set, we can conclude that A is open as well, according to the definition of open sets. So here I take let x from A. By taking x from A, we can directly go compare the images, because in Y we have the order topology. Order topology means we can compare, we can find two elements that we can compare with inequality signs. So here let x. in A, because of that x being A, we have this condition fx is greater than gx. Okay, so also note that these both uh, fx and gx are relies on y, because f and g both goes from y. But here they are given us uh, y has an order topology. Order topology means for any two elements in the space, we can find an open sets. Uh, let me put it this way. So this is just a side note. Let X be an order topology space. So if we can find AB in X such that we can compare these two elements with the unequal design, and also if we can just in case if we sorry, since we can compare these two elements, we can find due to the order topology we can find two open sets in X. Two open, this is the short hand notation I'm going to use in order to denote the open set. So let U open in X and B is open in Y such that A contains in X U, sorry, and B containing V. Also, all the elements that belongs to U, all the elements that belongs to U is greater than all the elements that belongs to V. That's basically the order what we can get from that Y being an ordered topology. So, but for this particular proof, for this particular proof, actually we don't need that last statement. Rather, the existence of two open sets are enough. So our next step is, since we found the two elements such that this condition satisfy in our main proof, now our A is fx and our B is gx. So these are the two elements that we found from the complement of S. So since fx is greater than gx, am I correct? Let me check. Yeah, fx is greater than gx. By the order topology, by the order topology, we can find two open sets such that U is open in Y now, because these images are belongs to Y, right? Y is the our order topology space that are given in, that is given in the question, and we also open in Y such that fx is belongs to U and gx is belong to Y, just by the order topology. Now, by the set theory, we know that if an image is belong to some set U, we can form the pre-image. So this called the pre-image of U. So X belong to the pre-image of U. This is a set. Actually, this is a set that lies in the space X, because F grows from X to Y. So all the elements that are in X map to Y. So pre-image is kind of a, we take a subset here and form, and we seek that what are the elements that are mapped to this particular set. So the pre-image lies in the domain, because usually this called the pre-image under F, so it belongs to domain because all the x's are here. So x come from capital X, that should be mentioned here, and x in G V as well. This is pre-image under G. So we can form this as, since x is belong to two sets, we can easily say x is belong to the intersection of these two sets. But What are these f and g? F and g are continuous functions. The question is given to us that in a way that f and g are continuous. So these are continuous function, and u and v by the order topology are both open in capital Y. That means the preimage of an open set under a continuous function is open. That is by the definition of continuous function in between two topological space, we can conclude that if a function is continuous by looking at the preimage of an open set. If the preimage is open, we say the function is continuous. Since the function is continuous, we can go uh, the other way around from the definition by concluding these two sets are open. Open in where? Clearly, these are open in X because these are subset of the domain, not the codomain. Okay, now we have an finite intersection of two open sets, which means by the definition of topology, this intersection, which means this whole set should be open in capital X as well. Okay, now we have found an open set of the domain that all the x's are comes from, which means we can conclude that x comes from our new open set, sorry, g, new open set, which is contained in the uh, the complement of is, which is a subset of X. So all the elements X's are come from an open set because this element is arbitrary. Okay. So that all the elements that lie in the complement come from this particular open set. So we can conclude this is open as well because all the elements that belongs to the complement all the elements that belong to the complement comes from an open set, which means the original set also should be open. So since this is open, we can easily conclude that the original set which we considered is closed in X. So that's the first part of the proof. Okay, now let's go back and see what they are asking for the second proof. Okay, usually in this kind of a function can be found by using the pasting lemma. Okay, so by the pasting lemma we can find one continuous function uh, by using the continuity of two functions. Okay, so let me tell you how should approach that problem. So in B, uh, actually, let us consider our clause set this one x. F x is less than equal to in we prove that this is clause in X, right? In part A. Similarly, we can prove this particular set. Just interchanging F and G as closed as well. By using the same method, you can prove this set also closed. Okay, now one can easily see the capital X can be given by taking the union of these two uh, sets because it's obvious, right? Because it's obvious because I mean it's obvious fact. Okay, so but when we take the intersection, we have x's that is agree upon the intersection under two functions. So this is a one condition for pasting lemma. This is another condition for pasting lemma. Here, in order to use pasting lemma, we have to form two clause sets. So we have found two clause sets, and the union of two clause sets should form the original space that also satisfied here. And upon the intersection of these two clause sets, functions should agree. So these functions should agree upon the intersection as well. So that condition also satisfied. If these three conditions are satisfied, find we can find a continuous function such that it is equal to uh, fx and gx. Here the question asks about a minimum, right? Because we can form a maximum also. Ask a minimum here, minimum of fx and minimum of g. Okay, so by pasting lemma, the continuous function always equal to the two functions under when x is belong to s and when x is belong to s dash. So here we take two sets we are considering in order to find whether this h is a minimum of these two. Look whether sets. Okay, so if x is belong to s, which means this one, right? So fx is the minimum, that is okay. Then when x is equal to x belongs to s dash, again gx will be the minimum. So this is also okay. So we have found the continuous by the pasting lemma. This is continuous by pasting lemma. This is continuous, and this is just saying the hx equal to just the minimum and minimum of fx and gx. So that's all about this question. So I will see you soon in another video.